Hello guys, this is a video where I will try to explain the theory behind the cell packed data. Normally when you create a cell bitmap, usually it's unpacked, it's raw pixels, uncompressed. It can be palletized, it can be raw 8 bit per pixel or 16 bit per pixel. But there is another format which it's really useful if you manage to generate the packed data. It's the packed format, and normally in the cell flags you can just enable the packed bit to make the cell engine interpret your cell data as packed data. But that, if you have unpacked data in your pointer, then this is not going to work. You have to also manually pack the data or use a tool. And I'm going to show you how the packed data are interpreted. So you could maybe write a tool to pack your own data. Also, I have code that I'm going to present at the end of this video that does the same. And I will try to focus in this video showing you the theory with some slides I have created. And I'm not going to write any new code. Maybe in another episode I'm going to try some interesting things I thought for effects based on the packed data. But now I'm going to show you some examples and some code at the end, and I will focus on some slides in the beginning. So here is the page where I found information on how the packed data are interpreted by the cell, so that I could write a function that takes as input unpacked data and then generates a packed format in the way that works with the cell. And I went through many iterations until I make it work. It seems easy at first because it's just a run length encoder where you can say take this pixel and repeat it so many times, or read the next n pixels that are different values once and output them, or repeat the transparent pixel 20 times, or just finish that bitmap line and go to the next one. But there are a lot of weird things, especially if you work with pixel formats that are 4-bit per pixel or less, because the way the bits are packed is not ideal. They try to pack bits very close, and some values are misaligned between 2 bytes. So there are things there that you have to take care of. And finally, another thing, when you create packed data, every bitmap row has different length, because one bitmap row might have very easy to compress pixels, and so it might be very short. The next one might be much bigger in size, in total size in bytes, or actually words, 32-bit words, because the length has to be 32-bit words. It has to be like 8 bytes, 12 bytes, 16 bytes, multiples of 4, and no less than 8. That's another kind of restriction. That's the same as the W offset stuff. When we were calculating, even for an unpacked bitmap, the total length of a bitmap row, but on an unpacked bitmap, that length was constant. But here it's going to be variable, as every line might be packed differently. And that's why when you make a packed cell, only the first preamble matters. Because you want to know, the cell engine needs to know the number of the vertical count, the number of rows in the cell, -1. So it knows how many packed bitmap rows to interpret before it finishes. And but each bitmap row has variable length. So this W offset here, that goes for the unpacked bitmaps. It's not gonna work with the second preamble. You can scrap the second preamble. It's not read. But the first one, you need the CEL engine needs to know that. It needs to know the uncoded and coded. The uncoded is without palette. The coded is with palette. It needs to know the bits per pixel to know if it's going to interpret pixel as 4-bit, 8-bit, 16-bit, and so on. Okay, so the first preamble is needed. The second preamble might not be needed. You could even scrap it from your CEL, as far as I know. So now it might be time to start showing you the slides I have prepared. So, yeah, as I said, to enable the CEL to interpret your data as packed data, you just have to enable the CCB packed on your flags. I do it with an OR. This is the only thing you need to do it. But this will not, of course, this will not magically pack your data. You have to pack it yourself, or you have to use a tool that takes unpacked data and creates the compressed, the packed ones with the format that the CEL expects. And that's what I'm going to explain here. So each bitmap row starts with an 1 or 2 byte W offset. That is an offset that points to the next packed bitmap row, so that we know that this bitmap row, maybe it's 12 bytes in length or 3 words, so that it knows how much to read. And that's the size of the packed data. That's not the size of the unpacked data. Maybe your unpacked data is 64 bytes, but maybe when you pack it is 12 bytes. It has to be word aligned. So if you packed it and it was 11 bytes, you have to pad it with 1 byte to make it 12 bytes, divided by 4 exactly. And why is it 1 or 2 bytes? Because this W offset is very similar to the one in the second preamble. The one, if your bitmap was unpacked, so uncompressed, then it would have a stable length in words of each bitmap row, but now it's unstable. So now the same logic that applied in the preamble, you apply it for every bitmap line. But every bitmap line will have a different W offset value. I might not spend much time explaining the W offset, because if you have worked, I guess if you have worked with CELs, normally you create a CEL and the W offset is created for you. So it is a bit complicated, but you might be able to see later my code for that. But that number, there are two different numbers. It depends. If your bitmap is of 8 or 16 bits per pixel color depth, then it goes to this category where the bits 16 to 25, this is occupying the second byte from the left, the first and the second byte, the highest byte and the second highest byte. That's why it's 2 bytes if your bitmap is 8 or 16 bit depth. And if it's 6 or less, it says G, but it's a 6. 6 bits, 4 bits, 1 or 2 bits per pixel. If the original bitmap is of that color depth, then it uses the highest byte from bit 24 to 31 on the flags. no, of the second preamble word, you know. It uses that byte, so that's 8 bits is 1 byte. So that W offset, even in the packed format, for every scan line separately, it follows the same logic. And I'm going to say the value is the number of words, the number of 32 bits minus 2. It's like that. It's some kind of restriction of the cell. So if that W offset goes 0, that would mean 2 words. That would mean 8 bytes. So it starts from 8 bytes, then goes to 12 bytes if the W offset goes 1, 16, and so on. There is a minimal size. And if you have a length that is less than 8 bytes, you have to put it in that space and pad the right side with zeros. And that's it. And there might be even padding if you have a higher number of bytes, but it's not aligned with the 32 bits. But anyways, let's move to the most important part, which is the interpretation of the bitmap data. And so when you start packing data, there is a 1 byte header. There are packets of data actually, and each packet has 1 byte header plus following bits of data. And I will say what I mean bits, because if you have some 4 BPP pixels, 6 BPP pixels, the way the bits are packed, there is no padding to fit a byte. Okay, they are very packed together, and it's a bit annoying if you want to make a packet depacker for that. But the important thing now is the byte header, and that's the byte header. Now this square are the bits. There are 2 bits and 6 bits following this byte header, and then the data are just, I put some random squares to indicate some random data I will explain later. And there is a 2-bit specifier. It's called 2-bit specifier in the docs, which describes what kind of packed data are following. If you need to repeat 1 pixel, if you need to create transparent pixels, or repeat a series of pixels. And there, the 6 bits are the count, are the how many pixels are following, and the value of a 6-bit number is from 0 to 63, but you add 1 in this interpretation. You add 1, so a value 0 would be 1, so that it goes from 1 to 64 pixels, because it would be pointless for someone to put 0 and that means repeat 0 pixel. That means nothing. So the maximum you can repeat is 64 pixels, and if you have a much bigger bitmap, maybe the same color that repeats 200 times, you have to split those packets to 64, to a series of 64 pixels. We will see that. So here is again from the docs the 2-bit specifier. You see the 2 bits, there are 4 combination of those bits, and then the 6 bits, how many pixels, it's the count of the pixels plus 1. Okay, and then the pixel data follows. So pack literal 0, 1 means, okay, I'm gonna give you the count, of course, and that means after this byte here you have a lot of unpacked pixel. This is if you have pixels that change a lot frequently, so you cannot pack them into a format that says repeat the same pixel many times. So you give, we will see that you give a series of pixel data in an unpacked format, and here you say the next 20 pixels, for example, read 20 pixels from the following data. The pack repeat is the most optimal. If you have a pixel color that repeats many times, you have a solid color that appears 20 times, then you will have the count on the first bit, that is 2 bits and 6 bits. You can fit the count 20. Actually, it will be 19 because it's plus 1. If you put a 0, it means repeat 1 pixel. If you put 19, it means repeat 20 pixel. And then the following pixel is 1 pixel. You just give 1 color. Instead of giving 20 bytes, if it were 8 bpp pixel, you would give 20 bytes in a series. You give 1 byte. 1 byte for the header and 1 byte for the pixel, and you have backed this enormously. And the same logic is for the transparent. If you have a sprite and on the left side there are 30 pixels that are transparent, again you put the count, you say the next 30 pixels are transparent just in this 1 byte header. And this one is even better because you don't have to follow it with pixel data, because you already told it. The next 30 pixels, it's just don't render them, skip them. Which is really, really good for sprites that have big transparent areas. And finally, to finish the bitmap line, to tell the CEL engine that the pack data for this bitmap row are over. It's done, go to the next one. There is the end of line, which is 0, 0. So if you put a 0, it's gonna terminate. And that one doesn't even need the rest of the 6 bits. Now, I think you might have to give fill 6 bits to pad it at the end anyway. Or that's a maybe. You might have to pad the line at the end anyway. So these are, they will be ignored. By the time it will see those 2 bits as 0, it will know it's over. It just needs to know where to jump next by the W offset that you give before the series of the whole package. And that will be fine, as the next bitmap line is 32-bit aligned. We will see about that. So now we will see some examples. And here I have 6 pixels that every pixel is different, it's a different color. So the best format for that is the pack literal, of course. Which is, okay, 0, 1, this is pack literal. Then the 6 bits, this is 1, 2, 4. If you convert it in binary, it's 1 plus 4, it's 5. It's 5, but there are 6 pixels. Yeah, because this number, you have to add 1. And that means you tell the CEL engine the next 6 pixels, read them for the data sequentially. So you have the pixels as they are, and you have 1 extra byte for the header. So that's a bit of a loss compared if you have this pixel unpacked. But if you have many series with literal and then repeat sections and so on, overall you might win. So you might have a bitmap with big areas of pixels, like here actually, the repeat. You might have 6 pixels in a row, that is the same pixel, the same color. So you give again, see here, the previous example, 6 pixels again, but it's pack literal, and this one is pack repeat, 6 pixels, but now the following data is 1 pixel value. And that could be, by the way, it depends. It could be 8 bit per pixel, it could be 1 byte, it could be 16 bits per pixel, it could be 2 bytes. But this header will be 1 byte, and the following data are minimized. Instead of 6 bytes, let's say, if that was 8 bits per pixel, it's 1 byte. So that's much better for this case. And then you have the transparent. Now, to make the case more complete, I have the 6 pixels where the first 4 pixels are transparent and the next are different pixels. Okay, so now the first packet has this header, pack transparent, and this binary is 3 plus 1, 4 pixels. It tells the cell the next 4 pixels are transparent, and there are no extra data. So 1 byte is compressing 4 transparent pixels. In an unpacked bitmap, this would normally be the 4 bytes in an 8 BPP bitmap, for example, where the value would be 0, would be RGB000. In a regular bitmap, if the color is total black, RGB000, and if you have set other flags, then it's going to be transparent with the background. And sometimes you might have a bitmap where the outside you want it to be transparent, and some inside elements of the bitmap, inside the graphics, they might be too black. Okay, and they might also create holes in the background, and so you make these ones to be not entirely black, but you know, a bit of blue, 0, 0, and 1 blue, so that they don't create holes. So you have transparent at the places you want and not. But if you use a packed format, this is another way to define transparent pixel. You could disable the transparency on the RGB0, the total black, for some parts of your bitmap, and you can have some pixels that you want with the packed format. You can make them transparent. Okay, even if this could be pixels that normally could be magenta or something, but you can, it's like saying skip those 4 pixels to the, with just 1 byte header, you say to the cell engine with the packed format, skip those 4 pixels. It could be 64. It could be making things much faster. So the cell engine doesn't even have to read the pixel and then decide, oh, that's not absolute black, so I'm going to have to not render this one. I'm going to have to do it to make it transparent. It doesn't even have to read those transparent pixels with the packed format, which is amazing with the packed format. And that's an example where I saw, okay, you have this header and then the 2 pixel form. So the continuation of the data is another header after this header that says packed literal. Okay, it has the value n, 1. 1 plus 1 equals 2. So it says the next data are 2 pixels that you just read normally, like regular data. And here I have another example where I'm putting everything together. So I make a bigger series of a bitmap line, and I'm going to even show you the end of line thing. And that could be the total length of our bitmap line. And you know, maybe the next bitmap lines are bigger. You can have variable lengths on your bitmap. You can have from smaller to bigger, or yeah, it's amazing. So the first 4 pixels are transparent. This 6-bit value is 3 plus 1, 4. No extra data needed after the header. The next header says pack literal 1 because it's 2 pixels. Because those 2 pixels differ, and it's not good. You could pack it as repeat, but it would be a waste. But because they are together and differ, you pack them as literal, and then you have next the data. I have the data here as blocky colors, because this could be 8 bits per pixel. This could be a series of 4 bits If it's 4-bit per pixel, that could be a 4-bit and 4-bit enable and enable making a byte. We will talk about how the data are packed very dense into bits. And then 5 pixels repeat. So you have the pack repeat. It's the same color repeating, okay. The value, that's 4. This is 4. So 4 plus 1, 5. And the following data is just once the pixel color that repeats, and not 5 times. So that's a great cooperation for that part. For this one, transparent, this one is great. For this one, you lose something, okay. And then pack literal, there is one unique pixel at the end, so we have to pack it as a literal. See, everything is 0 now. This 6-bit value of the pixel count is 0 because you always add 1, remember. So 0 plus 1, 1 pixel. There is no 0 pixel, repeat 0 pixel, it doesn't make sense. And then the color of the pixel. And then to close the bitmap line, we put the end of line 0, 0, and this, it depends. The docs sometimes say they might be, no, they always, they are not needed. It doesn't matter. But it says that sometimes you could, if you have some low bits per pixel, like 4 bits per pixel, 2 bits per pixel, maybe the last 2 bits could be 0, 0 if it fits the byte at the end. And you can close it here. You might not need to align it further. Also, the whole line has to be aligned by 32 bits. We will see that. So, and here we might see the pixel data, you know, that stuff that I just put like colors without explaining if they are bytes, if they are words, if they are bits. It's arbitrary. It's pixels. If it's 16 bits per pixel, then see, I separated every letter here is a bit. So there are 8 bits and another 8 bits. 16 bits for one color and 16 bits for a... So for these 2 pixels there are 4 bytes. If it's 8 bits, it's 1 byte for the first pixel, 1 byte for the second. And see, if it's... This is even on the unpacked. This happens even in the unpacked. And it can create some strange variation. It's easier for 4 bits, sometimes. Because if you have 2 pixels, you can have a high and low nibble, 4-bit each, and that's completing a byte. It would be tedious if there was a third 4-bit pixel, because you would have 12 bits and you wouldn't pad the byte with zeros. You would. I'll show you the 6 bits, for example. 3 pixels. See, I have put the same colors to the 6 bits, but there are 2 bits left on the byte. So this pixel, it uses the 2 bits and the 4 bits of the next byte. And there are 4 bits remaining in this byte, so it takes the third pixel and the 2 bits on the other byte. And now, do you remember the 8-bit packet header, the 1 byte? That header, that has to follow the next packet. Okay, this should not be byte aligned. This should be densely packed into the previous remaining bits. They did it like that so that they don't waste any bit, but it becomes tedious because now the next byte header or 8-bit header that describes the next packet, I have to place it to take the 4 bits of the previous byte so that it doesn't waste. It's not made up. That's how it's made. It's not made up that these are padded and then you start from here. Or at least I think so. I need to see that, because I might be mistaken. And oh my god, okay, let me see that. No, I think that's how it is. I wasn't sure if the packet header will start here, so if there would be padding. I think, seeing my code also and reading the docs, that it will force you. The cell will expect that the header will start on the, even if there is a gap before the next byte, it has to start here. It's not going to skip to the next byte. So if you have 4 bits and 6 bits and all that stuff, you might find yourself in the situation where you have to pack things densely, and even the next header might be misaligned, misaligned with the byte. So it might be tedious to write a generator. And this is something that will not happen. If you have 8 bits or 16 bits, the pixel data will always fill full bytes. So the next, the packet headers will always be byte aligned. But if you use, even in 4 bits, if there was a third pixel here, it will end in the 12 bit, 11th bit. So in the 12 bit, you would have the next packet and the next header. So it's kinda annoying. Although my engine, I think my engine can compress 4 bits and 2 bits. And I don't know if I ever wrote something for the 6 bits. I never used them. But anyway. So that's why I say more headache and closing a packed bitmap line. Because the way things are packed, and it took me sometimes to make it work. I was having failures with my generator. So you have this line, and there are 5 different types: the transparent, the literal, the repeat, another literal even if it's for 1 pixel, and the end of line. These are 5 headers, so they are 5 bytes. So we are assuming that these are 8 bits per pixel, by the way. And the literal will present 2 pixels as data, so 2 more pixels. The repeat will present this 1 pixel once, 3 pixels, and then the literal again this 4 pixels. So 4 pixel values in this whole line, and we assume it's 8 bits per pixel, so it's 4 bytes. So the total data are 9 bytes. But I think, if you remember in the beginning, let's see if we can get it. Before we start with this one, we had the W offset. So we had the 1 or 2 byte value that would tell you the length of this line, or it's really the offset to the next line, so that the cell knows where to jump to get the next data after it interprets this line. But in order to know this offset, you have to first do the work with packing the data, so that you know, because if the data are unpacked and you know the width, you know it's like it's 64 bytes or whatever, so you know what to put in the W offset. But if you are going to pack, you have first to pack them, so that you find out at the end that you have to go a bit backwards. You have to not calculate the W offset, to leave it for last. You have to calculate the packed data, and you realize it's 9 bytes, but I think the W offset, I need to check that. And I'm sorry for not explaining everything with certainty, but you can look at my code. I think it counts to the total length, because it's an offset to the next line. I think it might count. And I might be wrong here, but let's go on with this. And it could be, the W offset could be 2 bytes if the bitmap is 8 BPP or 16 BPP, which it is in the case, or 1 byte if it goes 6 bit or less. Now it's 2 bytes, so the total length is 11 bytes, and we might have to align it. We might have to pack it at the end with one more byte with zeros, so that it's word aligned. It's 12 bytes or 3 words. And the W offset is the number of words minus 2. So the W offset for that could be 1. The thing that we will write at the end. And when we start writing the next line pack data, we will have to jump 12 bytes later, for example. Even if that's not right, even if the W offset is not counting in the total length, it's a separate thing, we will still be at 9 bytes and we will still have to align it to 12 bytes. It's such a headache, man. But anyway, and just another thing. So, you are free to use whatever packet type you want. You want literal, for example, you could have this pixel, these 5 pixels that repeat, and you could say, I'm going to be unoptimized. I'm going to save them as literal because I want so. So you can choose different ways to pack your data, but the CEL engine will understand it. So you could have a literal for those pixels, and this pixel would repeat 5 times instead of 1 on the data. You could do that. Okay. Or you could do the whole thing as literal. Where it's transparent, put the black color, RGB 0. Or some index color that happens to be the transparent. So you could take the whole thing and pack it as literal and forget about compression. But have it in the packed format this way. It's a waste of size. So it's not like the CEL engine will pack it for you. So depending on the series of pixels, what I want to explain, there might be different decision on how to pack the data, and there might be something that looks more optimal, but ends not being. And I think my engine is trying to look at some of these cases, but maybe it's not perfect. For example, simple examples, and assume it's in 8-bit per 8-bit per pixel, 8 bpp pixel, 8-bit per pixel. This one, you can pack it in 2 ways. It can be a literal, 1 byte header and the pixel value. It can be a repeat, 1 byte header and 1 byte data. And the header on the repeat will say, and in the literal, we have the value 0 for the 6-bit count. So it means +1, it means 1. The next pixel, write it as it is or repeat it once time. So it's the same thing. So both of these methods will yield 2 bytes size for 1 byte pixel. So it's a waste, but if you have a lonely pixel, what can you do? So now you have 2 pixels, the same color. It's better to store this as a repeat, okay, because it's 1 byte header. And the 1 byte data, it will have this pixel once and say repeat this 1 pixel twice. But if you store it as a literal, you have to repeat the same pixel twice in the following bytes data, pixel data, and still have the 1 byte header. So it will take 3 bytes instead of 2. And see, I'm putting the red for this is more unoptimal in size than this one. And obviously this one that has different pixels, if you wanted to use the repeat, it could be 2 repeats actually. It could be 1 byte header say repeat, this blue pixel, 1 byte data repeated, and then it will be again another repeat header, saying now repeat this pink pixel, repeat it once and once. So it's 2 byte headers plus 2 bytes data. It will take 4 bytes. So this is better to store a sequence of 2 different pixels, to store it as a literal. 1 byte header to say I'm going to give you 2 pixels next, and just write them as they are. 1 and 2, 3. 3 instead of 4, and here it's 2 instead of 3. And here is the thing. So you would say, if the following pixels are, if 2 or more pixels are the same color, obviously it's better to use the repeat packet type. Not always, and so it depends. You have to analyze your data sometimes, because let's see this case. This is an ugly case where I have 2 pixels repeat, 1 lonely pixel, 2 pixels, 1, 2 pixels, 1, 2 pixels, 1. And one kind of packing is to pack this as repeat, because they are the same pixel, isn't it? You see, oh, 2 repeat pixels, the same color, you use the repeat pack. It's better, isn't it? And then one as a literal, L for literal, lonely pixel. 2 repeat, 1 lonely, 2 repeat. Let's use that. Let's alternate between the repeat packet or linear. Is this better, or is this better if we take the whole thing and make it 1 literal, 1 header byte literal, and then all of this pixel following individually? And see, here it is. Because of the header overhead, 1 byte per header, if you had small pixel that alternate, then you are wasting 2 bytes for this 2 pixel. 2 bytes for 1 pixel, 2 bytes, 2 bytes, 2 bytes. Because everything needs its header and the following pixel, other series of pixels to repeat, or the single pixel to repeat many times. And if you add this section is 16 bytes. But these are 12 pixels. So in this case, it's better to save this as a 1 literal pack. 1 byte header that says the next 12 bytes take the data uncompressed and write them. No pixel repeats, take them as they are, even if they have similar colors sometimes. And this ends up being 13 bytes. And I think in my packer, I'm looking at some cases where if there are 2 pixels that repeat, then I check if the next pixels are 2 pixels repeating, 3 pixels repeating, 4 pixels repeating. I might keep that, but if the next pixel it goes from 2 same pixel to 1 different to 2 same to 1, maybe it goes to 3 and 2 and 1. So there are variations that might pack better if you follow some other, if you don't always say, okay, if I see same pixel I have to use repeat. Okay, if you do a better kind of searching. So I will be deciding whether to use repeat or literal. Even with the transparent pixels, maybe I did something. If you have tiny gap of transparent pixels, although you can't do much with it. If there is transparent pixel, you have to use the transparent. So there will be some decisions to get a bit better compression sometimes. And maybe I don't have the best generator at the, maybe it can be improved, but I did some kind of such searching to decide for these 2 pixels depending on what comes next. If there goes a big row of repeating pixel next, I will continue with the repeat for this one and those ones. And that's it. So before I finish this, I could show you some old effects where I was investigating the packing engine. I have already uploaded this on my Experiments 3D Git repo, and I have already opened that for anyone who is wishing to learn from my code. And recently I tried to recompile and run it, and it was failing because I was doing things on the software 3D engine, which is also in the same package, and I would destroy the memory with that. So I'm doing some cleaning up. I'm adding an init. I don't need the 3D engine for the packed effects or the sprite tests, for example, but the rest of them won't. And I'm preparing to fix that. So by the time the video is up, all the parts might work well. But here I fixed it here just for this video. I'm going to run Phoenix because Phoenix tries to emulate the CEL engine bottlenecks, even though it goes a bit faster than what the original hardware would be. But you can see the difference between packed and unpacked sprites in the frame rate, for example. And I have two examples. The packed sprites are interesting. It takes some time. Hopefully it runs. Okay, it does run. So, I have many sprites that are unpacked. And you see there are some huge sprites with transparency. Let's remove, okay. Without the Vsync is 21. And here I think with the D-pad, no, I make them disappear. With the ABC, packed. Now everything is packed. Oh, it's still, where is, hold on. Still slow. It's hard to... Okay, I figured it out. I wanted to disable the Vsync and so to get some more speed and show how much faster or slower with and without the unpacked stuff is, but I forgot. When you set a background image with the sport, it's going to Vsync automatically, so you might not see that. So I'm going for now to... I'm going to disable the background so that we are able to see, because if you use the sport for the background erase with a bitmap, it's going to lock it at the Vsync. So, and the fact is, all these sprites, even when they are packed, they are going to be slower, but they're going to be faster if they are packed and slower if they are unpacked. But I couldn't see the difference. See, that's the thing. So now I have no background. Can I remove the Vsync? Okay, that's without the Vsync. So now we get 30 frames. And when I change it to packed, it's not, even in the real machine, it's not much better because I have a lot of stuff here. It gets 44 frames, you see. So when I change them with ABC to unpacked, you get slower frame rate. And let's see every one of these. Let's see this background. Okay. 16 bits per pixel, this pattern. It still goes fast. And now, when it's packed, it's faster. So when we have packed the textures, the texture reads are much fewer. And this because if you see it, now we see it at 60 frames per. A horizontal scan line here might be the same pixel. And there are big gaps with transparent pixels. The black one black side. So let's, which one is the next? Then you have this big, this is I think a 512 by 512 texture. Remove the Vsync. This is unpacked. So it's not compressed. 66 frames. You make it packed, it goes to 80 frames, not much more. Because it's huge and maybe it doesn't pack well. Make everything unpacked. So okay. The stars are, it's variable. 90, 83 unpacked. You pack them 140, much faster. This is slowing down things. Might have not packed well. This is the 4 bits per pixel. But those two, when they are packed together, 80, 90, when they are unpacked, they go under 50. So with the Vsync they go 30. Make them packed. So there is some gain, you see. Depends on how you pack the textures. And we might not have found the best packing, or the textures are too big, so might still not be ideal. And even in the real 3DO I never get. I must get the same, like 40 frames, 45 frames per second. And when I use the unpacked versions, now you don't see it. When I switch from packed to unpacked, I have an unpacked version with the uncompressed data, and I have another version with the packed. So I switch between the same textures in different formats. So there is surely an improvement. And I think now you might see the same with the rain example I was trying to do. That's something I haven't finished. Let's see. Oh god, it's even very slow. Unpacked, rain, a lot of layers. Okay, why the fuck is the same speed? Something is wrong with the... Okay, I don't know why this broke now. Everything broke. I'm so pissed. I'm preparing this video for a long time, and I'm not gonna spend more time for it. You have understood the core logic. I'm going to fix that till the video is out, and you can check the CEL packer. That's all I'm going to say. And I have a function. You are passing an unpacked bitmap. You are passing the data, width, height, bits per pixel, the type, if it's coded or uncoded, if it uses a palette. Maybe I could make a struct for that. And which color is a transparent color? This could be the value 0, or it could be the magenta, I think. It is going to try and spit out packed data. And you know, the other problem with this engine for now, I have a temporary buffer that is very big. Also now, I used to have a static array, and that would destroy the memory. But now you init the CEL packer engine, it allocates the memory, and then you deinit it at the end, and it tries to free it. Those arrays. And because it works on the unpacked bitmap, and it doesn't know if the unpacked bitmap is 64K inside. It doesn't know beforehand. because it needs to go through every pixel and starts packing stuff, and it has to store them somewhere. It doesn't know to allocate the buffer before. You might end up with 10 kilobytes of packed data at the end. So you have the, where is it now? Is the packed data? The temporary buffer, that is something much bigger. The whole process of the packing happens here, and it calls various functions that go through each pixel and go line per line, and it's counting the bytes and it's increasing. I'll tell you why there is a current bit, because it has to be dense into bits with misaligned bytes, and at the end of the time it knows the count bytes, and then it can allocate the packed data array that returns. But the things were written in the temp buffer, which we allocated with 256 kilobytes. That's enough of space. It was writing values in a temporary buffer, and then it copies the temporary buffer with, it finds at the end, okay, I packed this thing into 5 kilobytes. Copy those into the packed data and return it. And I even calculate the percentage of the packing, which I have an extend for my tests. And then you do need the CEL packer engine. You need the CEL packer engine for those temporary arrays that you might need. And then you do need, I think, for example, I don't know why this broke. I will see it later, but you need the engine. Generate unpack. Okay, that's some procedural generation of the layers. That has nothing to do with the packer, but here I have a new sprite function, and I have it on the sprite engine, a new packed sprite, where I give the unpacked rain bitmap, and it returns the sprite, and it also, yeah, let's see. I'm doing it on the sprite engine for now. New packed sprite. And here, create packed data from unpacked bitmap. I give the unpacked bitmap, I get, that's the pointer, the packed data, and I create a sprite with a new, this is a CEL sprite, and the sprite item I have, it has a CEL, it has CCB flags, and then I OR it with a CCB pack. After I gave the proper packed data, I say, okay, you are packed data now. That's how I have designed it. And the whole CEL packer is here. And I have the current bits because current bits, I'm counting bits as I go up. Because I have this that writes a value, writes, I'm passing the bits per pixel. To cut it short, this could write 3 bits, 6 bits. It could write irregularly in the way that the data are packed in bits. I just happen that to make it a bit faster, if the current bit is not aligned, I will run this, that would do some kind of loop and write bit by bit. Irregular, very packed bits. But if the bits per pixel is 8 or 16, they usually don't need, they don't cross a byte. They're not misaligned in bits. Then I write directly a byte value or a word value, so that I don't have to write 1 by 1 bits and it's very slow. Only in the cases where you write 4 bits, 6 bits per pixel and so on. And this one, or write one value, see, write end of line, write pixel repeater. See, here I write the header. This is the 8-bit header. This is the 1 byte header. 8 bits, but I call that just in case I was in some 4 bit per pixel, 6 bits per pixel, and it had to be split in the middle of the byte. And you see here, the type shift left 6, so it's the higher 2 bits. The type is the higher 2 bits. And these are the pixel repeats -1 and 63. Because if there is 1 pixel repeats, the value is 0. For the rule to do +1. See, it's what I explain in this. I'm doing some padding, taking care of all that stuff. This is the W offset I write. If it's 8 bit per pixel, it's a 16-bit value. If the BPP is 8 or higher, if it's lower, it's that this temp buffer is a unsigned char. It's an 8-bit. There are some stuff there, but it mostly works. And I'm going to fix the things I have broken by writing my software 3D engine and never testing if I broke other stuff for a long time. And anyway, guys, that's it. See you.